All right, so Amanda continued moving figures. The diagram at the right shows an image of ABCD. Look carefully at the correspondence between the vertices. Now, vertices, the word for corners. Can you rotate or reflect the original square to make the letters correspond as shown? So what we're looking for is right now A is here in the top left corner. A prime is directly across from it. A is sort of on the outer left, where A prime is on the outer right. That tells us that this is a reflection because the one on the outside stayed on the outside, also because they're directly across from each other. So if you wanted to put, say, a line of reflection down the middle, you could say, yes, it is definitely one or the other. And in this case, it is a reflection. If you can reflect, where would the line of reflection be? So it should be vertical so that when you connect A to A prime, it's at a 90-degree angle, and it should be equally split between the two squares. So vertical line, and it should be halfway between the two squares. All right. This time, Amanda rotated ABCD by 180 degrees about the point as shown. Label the vertices of the image on the right. And if you're having trouble, try using tracing paper, or like I had said before, wax paper will work as well. So in this case, we're saying this B is rotating and it's going to end up right here as B prime. So think about the direction you're going around the square, A, B, C, D. I'm labeling it in a clockwise rotation. So if B is connected to B prime, and you can see that they're connected, right? A, B, C, D goes clockwise. So if this is B prime and I go clockwise, this has to be C prime, this has to be D prime, and then come back around to A prime. The other thing that you can do is actually rotate your paper. So A is in the top left corner, and if I rotate it 180 degrees, you can see that A prime is still in the top left corner. That's another option, is to physically move the paper that you're working with. Reflections, rotations, and translations are all figures called rigid transformations. Rigid transformations of polygons do not change any of the measures or the angles or the side lengths. They stay congruent. The size, shape is rigid, meaning firm. The words transformation and translation, well, they sound a lot alike and they can easily be confused. When we talk about a transformation, that's just some type of change, any type of change. Whereas translation was specifically a shift or a slide. And you do just have to pause for a moment when you read it and say, is something transforming like a transformer? Well, those change. Sometimes they got, a different shift on the arms. Sometimes they got a shift on the tires. Sometimes they, folded in half or unfolded. They did some sort of change. Whereas to translate means you shift from, say, one language to another. Examine A, B, C and A prime, B prime, C prime in the graph at the right. Describe at least two different ways that you could transform. So two different ways that we could change to get from this one to this one. Now, when I look at it, I can see that this one has side AB on the left and this one has A prime, B prime on the right, which tells me I would probably do a reflection. And halfway would be right here. So first thing I would think of is to reflect over the line x equals 3. And then if I were to do that, C would be here, B would be here. So you'd have C prime, B prime. You'd still need to shift it down by 2 spaces. So then translate down 2 units. So if it were me, the first thing I would notice is that one has definitely been reflected. It's been flipped over a line. I would flip it over the middle, like the center line between the two, and then say, how many do I shift up, down, left, right from there? Another way we could do this would be a 180-degree rotation, but you'd want to rotate it, and this is what's the tricky part on this one. If you look, here is C and here's C prime, and this is kind of the halfway. If you were to rotate about that point, the way we just did with the squares above, like you can see how these are kind of connected, we could do, so this was 1, we're on 2. We could rotate about 0.33, 180 degrees. Doesn't matter if it's counterclockwise or clockwise. And then once we did that, we would also need to reflect it because the rotation would have it upside down. It would actually be pointing like this if we did that rotation. And so then we would need to reflect over y equals 2. You'd have a line here, reflect over y equals 2. I don't expect anyone to do the second one. I don't think that is sort of what people see first. I think the first one makes a lot more sense, to do a reflection where it flips and then a translation down. I think that one is a lot more accessible. The rotation one most people don't see, and that's fine if you don't. Having one way is plenty. Are there always going to be multiple ways to describe a transformation? Well, sure. There's always going to be multiple ways, because we already looked at the beginning of this lesson, the first video, we said you could do a reflection and a second reflection, and that gave you the same thing as a translation. So yes, you can always do 2 different rotations or multiple reflections. So we would say, yes, there's always going to be multiple ways. You could rotate 2 ways, right? Counterclockwise versus clockwise. Or you could do multiple reflections. There's lots of different ways you could do it, but that's just 2 options. Consider what you've learned about rigid transformations. Would a series of rigid transformations preserve the area of a polygon? Preserve meaning keep. So is the polygon going to cover the same area? And we would always say yes, because it preserves the angles, it preserves the lengths, so it would preserve the amount of area it covers. So we can say angles and lengths are preserved, so is the area. Size and shape doesn't change, so area won't either. If 2 polygons have the same area, they're always the image of a series of rigid transformations. And we can say no to that one, because there's a way to have the same area but be a different length or a different angle. Areas can be equal with different shapes, or say sizes. For example, you could have a triangle that's shaped this way, and it could end up with the same area as a triangle that's shaped this way, where this one has a right angle and the other one doesn't. And that would not be a rigid transformation, because it hasn't maintained its angles. So no, even though area is preserved, that doesn't always mean that the polygons are images of each other. Verify your answer to part A by calculating the areas of the original triangle EFG and its image E prime, F prime, G prime. So what we're actually looking at is, back on the first page, we had a triangle EFG. It had a base of 1, 2, 3, 4, 5, 6, 7, 8, and it had a height of 3. The other triangle that's there with the double primes, also base of 8, height of 3. So if we want to find out whether or not area is preserved, both of the triangles would fall under 1/2 BH, and both of the triangles we would do 1/2 times 8 times 3, which means both triangles would have an area of 12 units squared. And so, like, clearly the area not changing. We could also look at the hexagons from page 2. Did the hexagons from page 2 maintain their area? Sure. Hexagon area formula? No. I'm going to count squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 4, 8, 10, 12, 14, 16. Area also preserved on that one. So in both cases, area did not change. So area for the hexagon was 16 units squared for both. All right, so rigid transformation meaning any type of change. And then the 3 subcategories that we've been talking about are reflection, which was in section 311, rotation, and translation. So we have 3 subcategories under the big heading transformation.